Good morning, students. We'll be starting with DNF block elements. Now, before I start with DNF block elements, if you remember the periodic table, in that we discussed about it. What exactly are DNF block elements? They are mainly what we call as the transition elements and the inner transition elements. Now, when I talk about transition elements, the word transition was coined by the chemist Mendeleev, because when he made the first periodic table, at that time he had left a gap. If you people remember the old form of periodic table, right now though we have groups 1 to 18, but the old form was in Roman numbers. We had group 1 to like 1A to 7A, 1B to 7B. Then there was the group 8 didn't have any A or B, but there were 3 subgroups. So for those 3 subgroups, it is clear, he had coined the name transition elements, transit in between elements. Today we define the D block elements as the transition elements because they are placed one between the S and the P block elements. In the periodic table, S block, alkali and alkaline earth metals on the extreme left. On the extreme right, the P block elements, that is basically the aluminum family, carbon family, nitrogen family, like that till the halogen and the inert gases. That's group 13 to 18. So this block is in between. That's the D block, called transition elements, as the last 2 shells are incompletely filled. Outermost shell, that's the valence shell, and the second last shell, which is also called as the penultimate shell. Second we have is the F block elements. F block elements, they are the inner transition elements. Meaning of the word, they are actually placed inside the transition elements, but as there is no place over there, they are written separately because the last electron is not going into their D block. The last electron is going into their F block. In other words, the last electron enters the F orbital. For D block, the last electron enters their D orbitals. So that's why down separately, we have a series of 14 elements called the lanthanides and a 14 elements called actinides. Let's understand now. We will talk about one by one. Let's see over here. Please have a look at the slides. It's a totally conceptual chapter related to the periodic part. So main points I'll explain so you people will have a better understanding to see over there. Now the first part to discuss people over there. Yes. First we will say the D block. So in the D block people, when I'm talking, what exactly are the, what we can call as the groups that we have. So first we have the groups, that's group 3 to 12. That's one. That's a D block. That is from group 3 to 12, the 10 groups over there, because the capacity of the D orbital is 10 electrons. That's why we have the 10 groups. Then we have the F block, that is the 4F and the 5F, what we call. Is clear? That is the electron entering into the 4F orbital and the 5F orbital. Now in this D block people, if you observe, we have totally how many elements to check out. Means totally in the D block, if I have to say, how many elements totally will constitute? There are totally 40 elements, which we classify as the 3D series, 4D series, the 5D series and the 6D series. So just see on the slide please, the 3D series, as you rightly see, 3D series starting from atomic number 21, that is scandium, to atomic number 30, that is zinc. Then we have the 4D series starting from element atomic number, that's over there yttrium to cadmium, yttrium 39 to cadmium 48. Then we have the 5D series where it starts with first is La, lanthanum, atomic number 57. Then there is a void, 58 to 71 are the lanthanides, where the electron is not going in the D block but going into its F block. So they are written down. That's the lanthanide. So you have first over there nothing but 57 lanthanum. Then immediately next is hafnium, that is atomic number 72, and it goes up to mercury, that's atomic number 80. That's the 60. That's the 5D, sorry. And last we have, that's the 60 series, which starts from atomic number AC, that's actinium, atomic number 89, and straight away comes rutherfordium, that's over there nothing but 103, which goes till Cn, copper cenium, that's 118. So that's collectively over there the 10 elements. Now here the inner transition, that is the 4F and the 5F, rightly what you see, that's called the lanthanoids and that's called the actinoids. Why do we call them lanthanoids and actinoids? It's a prototype. Meaning of the word prototype, because they are coming from the elements lanthanum and actinium. where they have similar properties with respect to lanthanum and with respect to actinium. That's why series of separate elements called lanthanides and actinides. Please keep in mind, lanthanum 57, actinium 89, both in the periodic table, they are in the D block, because for lanthanum and actinium, last electron enters their D orbital, not their F orbital. Alright, that's one. Second comes, people, if you look at the last group, that is the group 12, that is zinc, cadmium and mercury. These are the elements of group 12. They have completely filled what we call as the D configuration. As they have the completely filled, configuration over there, what exactly is said over there? These elements technically should not be kept into the D block. Why? Because their D orbitals are completely filled. Still they are placed over there or regarded as the transition elements. Why? Because in their oxidation states, the electrons are in their D orbitals. So keep this, remember, elements of group 12, that is down the group, zinc, cadmium, mercury, their orbitals are completely filled. So their D is D10. So if the D orbital is completely filled, still they are kept into the D block. Why? Because they show properties of the D block elements in their oxidation states. In the oxidation state, electron belongs to their D orbitals. That's why we say, people, that all transition elements are D block elements, but all D block elements are not transition elements. That's one. Then moving on, people, to the next part, what we have. Next, we have to talk about the transition. The word transition, that's what I said, that was coined by the chemist Mendeleev over there. For the three triads, what I said, that's the group 8, 9 and 10 today we call. For that he was given. Then comes the general electronic configuration. This is important. Last two shells are incompletely filled. Outermost shell, that's N, and penultimate shell, last but one shell, N minus one shell. So last two shells are incompletely filled. So the entire configuration goes NS 1 to 2, N minus 1, D 1 to 10. So you have to read in the opposite way. NS 1 to 2, that's for the valence shell, S can be 1 to 2 S orbital, and N minus 1, that's the penultimate shell, the D can go from D1 to D10. Now the question comes over there, why is NS 1 to 2? If anybody recalls, you'll have done in 11th standard, structure of an atom, exceptional stability of copper and chromium, where chromium, atomic number 24, electronic configuration is argon 4s1 3d5. It should have been, according to Aufbau, it should have been 4s2 3d4, but it is 4s1 3d5. Why? Because of the less energy difference between 3d and 4s orbitals. As you go deep down in the orbitals, the distance between them goes on decreasing. Why? Because of the electron and the nucleus attraction, that's the nuclear pull. Because of the nuclear pull, the orbitals come more close to each other. No doubt there is also electron as well as nucleus repulsion also. But as the orbitals come very close, the difference in their energy level is so less that electron can violate Aufbau and jump from one orbital to another orbital. So we see in the entire, if you see all the 118 elements of the periodic table, you will see there are some 20 to 25 anomalous configuration because of electron nucleus attraction, that's nuclear pull, electron repulsion, as well as nucleus repulsion. So we have two exceptional configurations what we have in the 21 to 30 atomic numbers, that is the 3D series. One is for chromium, that's atomic number 24, that's argon 4s1 3d5. Second is copper, that's argon 4s1 3d10. Exceptional stability, where the stability rule says half filled and completely filled orbitals are more stable than incompletely filled orbitals. So that's the part. So this entire explanation is about copper and chromium part, what we see. Alright, then next, people, we have, now this is basically the series. I want everybody to understand this concept very well so that you get an idea to this, okay, which one and how it is. So just see this carefully, okay, everybody. Now the first one we have, that is from scandium to, this is the 3D series, scandium to zinc. A very easy mnemonic, how to remember this, 21 to 30 is all you need to know. Rest for all, you just need to know their start and the last. So for 3D, we need to know all 10. For 4D, first element yttrium to last element cadmium. That's all. You need to know the first and the last. That's all we need to know. You don't need to know the whole part. Same way in the next part over there. That's the 5D series. First La, then hafnium, and then straight mercury. Then comes actinium in the last one, that's a 6D series, then rutherfordium, and then finally UUB, or the name is now changed. Earlier it was UUB, there was a nomenclature, remember? Unbium means 112, un means 1 and bium means 2. So 1 bium 2, that way. Now it is copernicium. Now 21 to 30, mnemonic, listen to me carefully. Science teachers are very cruel, mentally fatigued, causing nightmares to cute Zuzu. The 10 elements: scandium, science; titanium, teachers; V, very; Cr, chromium, cruel; Mn, mentally; Fe, fatigued; Co, cobalt, that's causing; nickel, nightmares; Cu, copper, cute; zinc, Zuzu. The Vodafone ad, if anybody's seen, alright, those are the Zuzus. So I repeat the mnemonic, remember this. It's cursing science teachers, so you'll always remember, alright. Science teachers are very cruel, mentally fatigued, causing nightmares to cute Zuzu. That's one, alright. Then, moving on next, people. Now people, we are going to talk about certain concepts over there. Now these are the elements, that is zinc, copper, cadmium, that we said. Now these are not regarded as transition. This is what I explained. The reason is because in their oxidation states, electrons are in their d orbitals. Now in this lecture, we're going to talk about certain general properties. Now what are those properties? Electrons are, first of all, what are these properties? Let's understand this. One is we have a variety of oxidation states, what you rightly see. 1 minute. We see a variety of oxidation states, everybody. Then there is complex formations with ligands, then catalytic property and paramagnetic behavior also. Now the question is oxidation states. Now first of all, why so many properties are shown by all these d block? One most important feature, electrons are shared from two shells, the valence shell, that is N, as well as its penultimate shell, that's the last but one, N-1 shell. So NS orbital and N-1 d orbital, these two orbitals are involved. So as electrons are involved from two orbitals, we will see a variety of properties shown by these elements. Alright, so we will start with each one. Now see this part, what it says, some questions over here. These are with respect to the NCERT. Scandium is a transition element, that's what it rightly says over there, but it says zinc is not. I right now told you why scandium. Scandium is 21. Argon, whenever configuration is there, just draw the off bar. It'll be easy for you. And remember the atomic number is only 21 to 30. No other element. Scandium 21, argon 18, 4s2 3d1. d1 electron enters the d orbital. So it's a d block. Zinc, atomic number 30. Argon 4s2 3d10. Argon 18. First it goes into 4s. That's going to be 4s2, so 18 plus 2, 20, and d10, 20 plus 10, 30. So no electron in the d orbital is completely filled. So that's why we say it should be not. But why are we considering it? Again, in the oxidation state, zinc generally shows only one oxidation state, +2. So in the +2 oxidation state, zinc configuration becomes straight away. First electrons will go from its outermost shell. So it was argon 4s2 3d10. 4s goes. So in zinc 2 plus, electrons are 3d10 only. So electrons are in the d subshell. That's the reason why we say, or the d orbital. So as electrons in the d orbital, it is a d block element. That's what it says. Scandium, rightly it's 3d1. That's what you see here. Whereas on the other hand, zinc has completely filled 3d10 in its ground state as well as its oxidized state. Hence it is not considered. Clear? Alright, that's one. That's why I said no. All transition elements are d block elements, but all d block are not transition. Now let's see one by one all the properties. Now first coming with the physical properties. Now these are the metals. Basically d block has got mainly electropositive metals over here. Alright, so they have generally high tensile strength, malleability, ductility, thermal conductivity, and all these part, and metallic luster, where the exceptions are zinc, cadmium, mercury, and Mn. Now the question comes, all these properties, tensile strength, malleability, ductility, temperature, conductivity, all can be explained only on one condition. What is that? Metallic bond. We have discussed this, right? Metallic bonds. What metallic bonds? On the surface of the metal, if you pass an X-ray, you will see a sea of electrons. Those are the mobile electrons. Like for example, suppose I say aluminium. I have a sheet of aluminium and I pass an X-ray. On the aluminium surface, I will see the aluminium cations. Those are called as the kernels. Their positions are fixed. Now, aluminium forms Al3 plus by the loss of 3 electrons. So those 3 electrons don't go anywhere. They're just hanging above that aluminium kernel. So if suppose I have on an aluminium plate 100 aluminium atoms. So it's 100 into 3. There are 300 electrons on that small plate of aluminium. These electrons are the mobile electrons, and the force by which these electrons are attracted to the nuclei of the aluminium cation, that's called metallic bond. So how do you define metallic bond? Metallic bond is a bond or an electrostatic force of attraction between the positively charged cation and the free mobile electron within a given sphere of influence. Where we say more the number of mobile electrons, more the electrical conductivity, high melting points, high boiling points, then more you can talk about metallic luster. All the properties with respect to metals can be explained on the basis of metallic bonds. All right, one. Now what is given on the screen, if you observe, are basically the structures. We'll be doing this in the 12th in the chapter called solid state. HCP stands for hexagonal close pack structure, in the form of a hexagon. BCC stands for a body centered cubic structure. Now BCC is basically you have a cube and there is one atom at the center of the cube. That's called body centered cubic structure. That mainly is sodium metal. That shows that. And down we have one more to talk over here. That is what you see over here, CCP, cubic close pack, which has one more name. If anybody recalls, FCC, face centered cubic structure. Aluminium, where you have atoms at the corners as well as at the center of the faces. All right. So cube has got over there the corners as well as the 6 faces. So every center of the face also has one aluminium atom. That's called CCP or FCC. So this is about the structures. Next people we have, now I want to talk about its melting point and boiling points, where if you observe, just look at that. There are different series. Now this is titanium, vanadium, chromium, manganese, iron, cobalt and all that. So this is basically what I can call as our 3D series. Then zirconium, niobium, that's what you see, that's the second series, and the third is the third transition series. Now what is trying to say, the transition elements with the exceptions of zinc, cadmium and mercury, all right, are much hard and they have low volatility generally. Now these are the exceptions, again the same thing, electrons they have completely filled shells, that's why. Now generally their melting points and boiling points are high. Now the melting and boiling points are attributed to the involvement of, again, what is the logic of the high melting and boiling point? Electrons from 2 shell, n-1d and ns. So 2 orbitals involved, penultimate and the valence shell, both are there. And it says in any row, the melting point rises to a maximum at d phi, except for the anomalous part of Mn and technetium. And the logic of Mn and technetium having exceptions, Mn is manganese, Tc is technetium. For your understanding, technetium is the only d block element which is a man-made element. So anytime if a question comes in an MCQ point at JE or NEET, normally in lanthanides and actinides as we go above, if you all know, we have transuranic, that's above 92. Those are man-made elements. But in the lower series, all are generally naturally occurring except Tc, technetium. Remember this, that's atomic number 43. That's the only element which is synthetically prepared. All right, 1. And the reason for these having an exceptional or anomalous values is because of their complicated lattice structures. That's 1. Now what it says, Mn and have regularly as the size increases, they have high enthalpies of atomization. Now what is this high enthalpies of atomization? This is thermodynamics. Like for example, we say carbon in the solid state goes to carbon in the gaseous state. That's called enthalpy of atomization. Definition wise, or hydrogen gas breaks down to form 2 hydrogen atoms in the gaseous state. Enthalpy of atomization is the amount of heat exchanged to break a molecule to form its free gaseous atoms or form its free gaseous radicals. That's called atomization. They have high values of enthalpy of atomization. That's what it says. And the maxima is about the middle of each series, indicates that there is 1 unpaired electron per d orbital, favorably for strong interatomic attraction. Matlab till that part of D5, there's one electron is going, it says it increases till the maxima and then it decreases. In general, this is the important point. See here, greater the number of valence electrons, stronger is the resulting bonding. Since enthalpy of atomization is an important factor in determining the standard electrode potential, metals with high enthalpy of atomization tend to be noble in their reactions. So electrode potentials, you'll have seen that in redox reaction, the SRP series, where all metals are down and non-metals are up. You'll be seeing in the 12th in the electrochemistry part also. So the concept, because of their high melting and boiling point, is because of its enthalpy of atomization, with the exception one is group 12, zinc, cadmium and mercury. That's because of their completely filled shells. And second, we have Mn and technetium because of their complicated lattice structures. That's one. So this is one part over there. Then the next we have to talk the variation in its atomic and ionic sizes. That's in the transition elements. Now generally if you see S and P block, what was the trend with atomic size? Across a period, atomic size decreases. Matlab S block generally have the largest, and as it goes towards the P block it becomes small. And for inert gases we say they have a slightly bigger size than the corresponding halogen because of the electron propulsion. D block doesn't show that type of variation. Why? S and P block elements, people, together are called normal elements. Only the valence shell is incompletely filled. In D block, last two shells are incompletely filled. That is outermost shell and penultimate. So as electrons are involved from both the shell, observation is, if I talk about the 3D series, the size decreases from scandium till chromium. And post chromium, people, the size remains almost the same. That is because of the poor shielding effect. That's what is there. I'll just read out, just observe this carefully, what it says. New electron enters the d orbital. Each time the nuclear charge increases by unity. It may be recalled that the shielding of a d electron is not that effective. If anybody recalls, shielding effect, pull of the electron towards the nuclei. So if the inner shells electron are pulled towards the nuclei, force of attraction for the valence shell decreases. That's what we call as shielding effect. Shielding or screening effect. Shielding the valence electrons by the inner electrons due to the pull. By the shielding order, S greater than S electrons are shielded maximum because they are very near to the nucleus, then P, then D and then F. So the order S greater than P, greater than D, greater than F. Now what is trying to say? An interesting point over there emerges that atomic size of a series are compared with those of the corresponding elements of those series. The curve which shows an increase in the first 3D and second D, but the radii observe this point very clearly. But the radii of the third, that's the 5D series, are virtually the same as that of the corresponding members of the second series. So what is trying to say? That we have the curves where as one goes down, size is increasing. So 3D, 4D, 5D. 5D size should have been more than 4D because it's down the group. But 5D size is similar to that of the 4D. And if you remember periodic table, we spoke about lanthanoid contraction and actinoid contraction. And due to lanthanoid contraction, what is happening, people? If you observe, 3D was scandium to zinc, 4D was what we had as over here yttrium to over there is nothing but cadmium, 5D was La, then hafnium and then mercury. So now here in the 5D we have the F block coming in, where electrons are going into the F orbital also. Shielding of the F electrons, people, is the poorest. I just now told you the order S, P, D and F. So if the F ka shielding is the poorest, the valence electrons are pulled more towards the nuclei. So if the valence electrons are pulled more, people, the sizes of the 4D and 5D elements, if you compare, theoretically there should have been increase, but they don't have any increase. Their size remains the same. That's called lanthanoid contraction. So lanthanoid contraction is the electrons entering the floating lanthanides due to the weakest shielding of the F electrons. The valence shell is contracted, and because of that, if you compare the atomic size of 4D and 5D, the elements have almost the same size. And when we do F block, we have done this in periodic table also in 11th, there are 4 pairs of chemical twins. If anybody recalls, किसी को याद आ रहा है? Chemical twins, elements which have identical chemical properties because of their similar size, and the reason was lanthanoid contraction. Anybody remembers the pairs? The 4 pairs: zirconium and hafnium, niobium and tantalum, molybdenum and tungsten, technetium and rhenium. I repeat all the 4: zirconium and hafnium, then molybdenum and tungsten, technetium, rhenium over there. Is this clear? So the 4 pairs what we have of chemical twins which have identical properties. That's one. That's I've written over there what is about lanthanoid contraction. Then the next we have people, what we have to talk now. See this part. Now whatever tables are there, mind you, they will not be asking statistical data, but looking at this, they can ask you the orders if you observe. Like for example, they have gave the enthalpy change of delta H1, delta H2 and delta H3, where you need to see the orders when it is becoming half filled. Like for example in Mn, if you observe, then look at that variation, how it is increasing over there. And then Mn ka value is slightly more and Fe is lesser compared to that. So these variations is what will be observed over there. Alright. So in the third IE over there, these are the exceptions to be observed. Alright. That's one. Standard electrode potential, if you observe, all are with negative values except one in the scandium to zinc, that is copper. So if you see here, all are with negative values, meaning all are placed. Zinc is also with a negative value. All are placed below hydrogen. All are good reducing agents. They will readily undergo oxidation. Only we have one copper that is with a positive value, meaning copper is placed above hydrogen, meaning copper and cupric ions have more tendency to undergo reduction and deposit as copper metal. That's one. Then people, one more question there, as you rightly see. 1 minute. Why do transition elements have higher enthalpies of atomization? That is again people, they have more number of unpaired electrons that you see. So a large number of unpaired electrons are there. That's why they have strong bonding. That is the metallic bond. That's why. Now people, a question. In the series that we have scandium to zinc, it says the enthalpy of atomization of zinc is the lowest. Now the question is, why is the enthalpy of atomization zinc will be the lowest? Anybody can think of this? Please think over there. Alright, the answer goes this way. I'm reading the answer. Please pen it down somewhere in your rough books over there. Specify there. In the formation of metallic bonds, no electrons from 3d orbitals are involved. In case of zinc, while in all other metals of the 3d series, electrons from the 3d orbitals are involved in the formation of metallic bonds. That's why people, we say with respect to zinc has a completely filled orbital. So as there is a completely filled orbital, in zinc, electrons are not involved of the d orbital, whereas for the other elements, electrons of their d orbitals are involved. That's why zinc will have the lowest enthalpy of atomization. That's one. Then next people, we have over here what I was talking. This is the trend, what it says. If you observe in the trends of atomic radii in the transition elements, I told you it decreases till chromium, and from there if you observe, look at this trend. Their values have a very small difference. They are remaining almost the same. Alright, that's one. And here people have given one pair, zirconium, hafnium. I told you there are totally 4 pairs. Zirconium, hafnium. Then we have molybdenum, tungsten, niobium, tantalum, and we have over there one more pair, that is technetium and rhenium. 4 pairs of chemical twins. This is all about the poor shielding effect part, what is there, because the D and the F block, F shows the least shielding over there. So because of poor shielding, we have the orbitals getting contracted there. So with respect to D block, if a question comes, scandium to zinc, alright, what is the trend? It decreases till chromium, and from chromium it remains almost the same, or there's a very small change with respect to the atomic size. The reason, because of the poor shielding of their d orbitals. Alright, that's one. Next comes people, we have a trend, that is ionization enthalpy. We all know what's ionization enthalpy. The amount of energy which is supplied to remove the most loosely bonded electron. So we will have different IEs here, IE1, IE2, IE3, energy supplied to remove the first, second or the third electron. Now we all know normally order, if I have 3 electrons to be removed, the order is the third IE will be maximum, then second IE, and then the first IE. Reason, because as you go on removing electron, nuclear charge goes on increasing, and nuclear charge is directly proportional to ionization enthalpy. Hence the IE will be higher for the third, then second and first. Now here what it says, look at that. Due to an increase in the nuclear charge, which I can use the filling of there's an increase in the ionization enthalpy along the series. So across a period, it will increase from left to right. However, there are variations. Now that's what we observed over there. The first IE, all right. The irregular trend in the first IE of 3D is accounted because of the little energy difference between 4s and 3D. All right. That is one. Next it says the value of chromium is lower because of the absence of any change in its D configuration, and zinc is higher because of its representation in the 4s. Technically, people, if you see chromium, that's 4s1 3d5, and so that's the reason why it says over there, because of the any change in the D configuration, the value is lower, and zinc is 4s2 3d10, so that's completely filled, so definitely it will be higher there. That's one. Then now coming to the concept, the next point what we're going to talk is about oxidation states. Just an understanding, the common oxidation state we have, that's +2. That's for the general for all these metals. The 3D series, the common state is +2, and in 3D the highest oxidation state is of Mn. That's basically +7. So please understand carefully from MCQ's point. Listen well. The lowest oxidation state of 3D series, that's from scandium to zinc, that's +2. What is the maximum oxidation state of the 3D series? That's of +7. That's of Mn. That's atomic number 25. 4s, that's over there, nothing but 4s2 3d5. So it loses all the 7 electrons. So +7. Highest oxidation state of the entire 40 elements of the D block, osmium and rhenium, where more stable is osmium, OS. It forms a compound OSO4, osmium tetroxide, where osmium has the highest oxidation state in the entire D block of 40 elements, that is of +8. So MCQs be clear. Okay, that's one. Now this is the concept with respect to the half filled and how it forms over there, where it says in the lower oxidation state, the elements will be good reducing agents, and in the higher oxidation state, these elements are going to be better oxidizing agents. So reducing agents will undergo oxidation, so there will be an increase in the oxidation number, and the higher oxidation state elements will undergo reduction, that is oxidizing agent, there will be a decrease in its oxidation number. So that is one. What it says, yeah, the second IE usually are higher for, second IE will be higher with respect to chromium and copper because of the D5 and D10 configuration. Then, yeah. Now with respect to the third IE, it says things are little, what it says over there, the trend in the third is not complicated with the 4s and shows greater difficulty, but obvious people, third IE will be higher because nuclear pull is more over there. That is one. So in general it says the third IE enthalpies are quite high, and they are marked to break between the values of Mn2 plus and Fe2 plus, because Fe shows two states, ferrous and ferric. Then okay, this is one. So we're going to talk about the IE, and based on the IE we have over there nothing but a concept of oxidation state. This is the last feature for the day. So we have spoken about atomic size, we have spoken about ionization enthalpy. Now we are talking the last point, that is about its oxidation state. Now what is the part here? Just see the table carefully. You have to memorize this table because the values, scandium, common state. So if a common oxidation state is asked, if you observe, all generally have +3 state. If you observe, only copper doesn't have, copper is +1 +2. So this, it's like this, scandium +3, titanium 2 3 4, 2 3 4 5, chromium 2 3 4 5 6, manganese 2 3 4 5 6 7, that's the highest of +7, Fe 2 3 4 and 6, cobalt 2 3 4, nickel 2 3 4, copper 1 2, and zinc +2. Now here generally if you observe, as I said, the highest common state, that's of +2, what we see, +3 is also observed with many of them, +7 is the highest for Mn. Now here what it says, Mn is maximum, people, +2 to +7, that's one. That's the part over there. And people, stability wise we can say, okay, scandium +2 is virtually unknown, titanium 4 plus will be more stable than titanium 3 plus or titanium 2 plus. Why? Because in titanium 4 plus, titanium is 22. That's argon 4s2 3d2. It loses all 4 electrons, achieves the configuration of argon. So basically oxidation state stability will be with respect to half filled and with respect to completely filled. But certain places we will have exceptions also. Like for example, chromium stability is in +6 state. Is this clear? Is this clear? Majority compound, but chromium shows good stability in +3 also. Alright, where +3, if you observe 4s1 3d pi, one of the 4s and two of the 3d. So the configuration is technically argon 3d3. Now 3d3 is neither half filled nor completely filled. Still it is more stable. The reason is it's because of its attraction, that is the nucleus electron attractions over there, and also because of their what we call as their lattice structures. So because of their structures with whom they form compounds, on that basis the +3 oxidation state will be more stable. That's one. Now zinc in the state is +2 only, people. That's what we see because that's the maximum it can have. Now it says the maximum state for resonance stability, for reasonable stability to the sum is added. Like these are the oxidation states what you see over there on the top. So titanium in 4 with oxygen, vanadium with 5, chromium with 6, Mn with 7. We have seen, no? Potassium dichromate, potassium permanganate. So in dichromate, chromium is +6, permanganate, Mn is +7. That's the part because of the stability rule. Now it says the variability of oxidation state. Characteristic transition element arises of, again the same part. It depends on their different orbitals which are involved, and it will also depend upon the stability rule, what it says. Yeah. Now what it says, look at this. Interesting feature in the variability of oxidation state of D block is noticed among the groups, that is group 4 to 10. Although in P block, the lower oxidation states are favored by the heavier members, right? This we have discussed in the P block. If anybody remembers inert perfect, remember, no? Group 14, NS2NP2, +4 state is more stable, but as you go down lead, stability is more in +2 because the last NS2 electron behaves chemically inert because of the shielding effect part. Same way, aluminum family, last element thallium shows more stability in +1 state rather than +3 state. So here it says, compared to that P block part, here it is exactly opposite. What it says? The opposite is true in case of D block, where it says in the higher oxidation state, the compounds are more stable. There the oxidation states in P blocks as you go down were decreasing. Here as you are coming, as it says over there, as you are coming down, those oxidation states are becoming more stable as one goes down the group. So look at that in group 6, molybdenum and tungsten, the oxidation states are more stable in +6 over there, that way. And similarly it says then chromium, which is in +6. Chromium in +6 is a dichromate, that's an oxidizing agent. Same way molybdenum and W is tungsten, they are not. Lower oxidation states are found when complex are formed, like for example ligand. Remember these two complexes, NiCO4 and FeCO5. Here the oxidation states of the metals are 0, matlab they are not losing any electrons. That's because carbon monoxide is a strong field ligand. So the strong field ligand will push the electrons to get paired in the lower shells or the low energy levels. So that's why nickel and Fe will not lose any electrons. So the general trend, oxidation state wise, we say it's because, so if I have to put a simple thing, oxidation state depends on what is oxidation state? The net apparent charge assigned to an element in its compound. Minimum oxidation state pertains to electrons of the ns orbital. So for 3D, the electrons of 4s orbital. Variable oxidation state pertains to electrons of the ns orbital, that's the valence shell, plus n-1d orbitals of their unpaired electrons of the n-1d shells, that's their penultimate shell. Very important point, I repeat. Minimum oxidation state pertains to electrons of their valence shell. Variable oxidation state pertains to electrons of the valence shell plus unpaired electrons of their n-1d penultimate shell. That's how we have the table part. Alright, that's one. Now, people, the question part over there, a transition element which does not exhibit over their variable oxidation state, then that's nothing but scandium what we have, it doesn't show. And it says which if the 3D series elements exhibits the largest amount of oxidation state. People, 3D series, that's scandium to zinc, maximum is Mn, that's +2 to +7. Alright, till here this much now. Next class we'll discuss about more properties. So my suggestion from the NCERT part, just try reading, or with these slides which are there, just with these PowerPoint presentations I'll be sending you separately also. Just read these slides over there so you get an idea okay, how the trends are. Alright, we'll continue with the trends in the next class. Thank you.